So, hello and welcome. My name is Michal Valint and I'm from Guerrilla. And today we'll be talking about rendering technology of Killzone. Well, I'm really happy that so many of you made it here. I guess there was a lot of good parties yesterday and this is quite early. So, I hope not a lot of hangovers out there. What we'll be talking about? Well, Killzone 2 has been in development for somewhere around 4 years. Yeah, we know it took us some time and we didn't start well. But of course, the benefit is that during these 4 years, we tried a lot of rendering techniques, and some of them worked, some of them didn't. Some of them even made it to the final game. And this is actually what I will be talking about. I will try to give away some of the optimizations that we made during these 4 years that might be useful for your next game. And what to start with? Killzone 2 is very light heavy. We have a lot of dynamic lights. That was always our target, so we needed to come with a rendering technique that allows us to do so, and that is deferred shading. For those who don't know what it is, I will have a quick introduction, and for those who are afraid that every morning where they open the fridge there will be something about Killzone 2 and deferred shading, bear with me, it will be short. The next thing is memory optimizations for our render targets. Well, you of course know by yourself that as you develop, you add some stuff, you add more memory, and at some point you discover that you allocated 60 megabytes of your render targets, of your memory just for render targets, and it just doesn't work like that because you cannot fit textures there. So what you do, you take a step back and try to compress the hell out of it. That's what we did. That's what will be the second part of the talk. And then, of course, it will happen that you cannot hit the 30 FPS again because artists just tend to put a lot of lights into the level. We told them to do so, so they did. And yeah, that's how your promises usually backfire. So we had to spend enormous amount of time trying to optimize our lights. And that will be the next part. And at the end, I will talk some more about how we allocate memory for our SPUs, because we use SPUs for everything. There was talk about it by Michiel, and so our entire engine is working out of order. We don't really have some clear sense of where is the beginning of the frame, where is the end of the frame. So for all the rendering data, such as vertex buffers, some runtime textures, all the temporary data that are required only for the frame, such as scene graph query results, buffers for that, and of course the push buffer alone, we need to have an allocator system that allows us to allocate in parallel and free the memory as soon as possible, and that will be the last part of the talk. At the end, we will of course have some questions and answers. So if you find something that you would like to ask about at the end, write down a note. We will have time to answer that. So first, what is that deferred shading? Well, let's first answer the question, what is it not? It's not the standard rendering that we internally call forward rendering, where you just start to push triangles onto the screen. So you take a triangle, rasterize it, put expensive shader on it, where you load all the materials, then you load all the light properties, then you try to compute the final pixel value color, then you output it into the back buffer, and you repeat this for every light you have. If you try to be smart, you try to group the lights to not read the materials too much. But then you end up with the madness of all the shader combinations and the problems with shadow maps. So we try to do it differently, and that's this. Instead of rendering the scene and the lighting in the same pass, we actually separate scene rendering and all the polygon complexities from the actual lighting. Lighting comes later on. It's very similar to actual like post-process in some of the DCT package. And this allows us to use huge amounts of lights, as I already said. The thing that we fill, that we actually do during the scene rendering, we fill a structure that we call gbuffer. Gbuffer is pretty much all the material informations that you need to do lighting. You store them in this structure, which is screen sized, and is usually just collection of render targets, and you allocate each channel for something that you need, like normals, depth, or position, your diffuse texture, your shininess, your specular powers, whatever you need to compute the final lighting. And this all happens in the single and the last pass where you actually deal with scene geometry, and that's called geometry pass. Later on, you approach the lighting pass where all the magic, all the post-processing happens. So you have this scene. It's already partially lit because this is not the first light that is applied to it. And we are going to try to apply lights here. So what we do, for each light, we actually find all the pixels on screen that are within the area of influence of this light. And for each of these pixels, we read the gbuffer, compute the pixel intensity, the lighting, and that we output to a backbuffer. And we do this for every light in a scene, in a loop. The good thing is that it doesn't really matter how complex your scene is. You do this in image space, so the only thing that matters for your performance is how many pixels your lights cover. And also, it doesn't really matter if the lights intersect or not. You just add them on top of each other. You can share memory because as you render lights in sequence, you can just use the same memory for shadow map and just override it again and again. It just makes the whole engine very simple and straightforward and actually very easy to extend. Of course, this is not the end. After this, we need to render the transparent geometry because deferred shading doesn't actually support transparent geometry. So we have a pass with standard forward rendering for transparent geometry. We have some low resolution rendering going on for particles, and then we have, of course, post-processing where we put this all together. So I talked about that gbuffer, I talked about positions, normals, and you might think, yeah, cool, we just used floating point buffers. And you are right, it's the best option, and we've been there, and we've ditched it, because it's just too much. You have too much memory. The GPU is, of course, slower with floating points. It has to do more stuff. The bandwidth is much higher. And as I said, we were not able to actually hit 30 FPS, even just because of this. So what we did, we took a step back and looked at it and said, like, oh, but this is what we can remove. This is what we can compress. So this is what I will be talking about. The first thing that allowed us to do so is that we don't really have any HDR lighting. Our artists, they're really, I would even say, control freaks. They just want control of everything. So if we just came in with, yeah, here is this cool tone mapping, it's automated, they would just say, no. So we just made them a nice color correction filter. You saw it yesterday probably. And yeah, they do really nice desaturation with it. So we could probably go away with the grayscale rendering in the end, but we didn't. So in the end, we were able to move away from FP16 buffers, and we filled 4 32-bit RGB8 render targets, and we use depth buffer, so it was just over 18 megabytes. And then we said, like, yeah, okay, it's quite low, so instead of 60 megabytes, we got to 18. That's pretty cool, so let's just put some anti-aliasing there, so then we can go to conferences and talk about it all the time and act like we are very cool. We are not. It's very funny. And of course, to further optimize the memory, we try to reuse this gbuffer memory for everything we have. So if we have forward rendering at the end of the pipeline, or we have HUD, or we have some map on-screen map with multiplayer, or post-processing, we just use the same memory that we used for gbuffer, because it's just not necessary to have it around at the end of the frame, and that way we kept our memory quite small. So I don't know if I mentioned it. We don't have a dedicated position buffer. We reconstruct our positions from the depth buffer, and we used to have it actually. It was pretty nice because we wanted to use to create some nice displacement effects, but it just didn't materialize. Artists didn't make shaders for it, so we just removed it. Didn't tell anybody. Nobody was unhappy. And of course, we do not have space to store all the normal components. We store view space normals, only X and Y components, and we actually compress FP16 values into the RGBA buffer. You can see the CG instructions for it. It's actually pretty nice trick, so might be useful for you. And yeah, we don't have negative Z, which is usually not a problem. You could see that the glazing angles that probably normal should turn to negative there, but I dare you to find it in our game. It's just so hard to spot that I wouldn't advise anybody to spend time on trying to find a solution where to put it. And then we have motion vectors there, which is just screen space velocity for post-processing. We then later on read it, downsample it, blur it, and use a motion blur as Michiel was talking about yesterday. Now, of course, I was talking about gbuffer as primarily the material buffer. So we have, of course, some material properties there. We have albedo, which is pretty much our diffuse color, but it can actually be anything, because as with all the shaders we have in game, they are all authored by artists. So whatever they put into albedo is what they want. So it can be procedural, whatever they want. The same goes for all the other material properties. We have material roughness, which is our fancy name for just specular exponent, because we store it in log space to actually have some more precision for low exponents, and hence high roughness. We have most of the surfaces are pretty diffuse. Then we have specular intensity. You might notice that as a single channel, we do not have actually per material specular color. It was never necessary. Artists just used shades of gray, so we just removed it completely. Nobody was bothered with it. And then we have something rather cryptic called sunlight shadow, which is our pre-rendered direct shadow from sunlight. We store this information in light map for static objects, and we later on use it not only to enhance quality of the real-time shadows a bit, but to actually highly optimize the shadow, the sunlight rendering in our lighting path. I will get to it later. And the biggest or most important part of our gbuffer is actually called lighting accumulation buffer, and it's just a fancy name for our back buffer. This is pretty much where all the light contribution gets accumulated, and the reason why we have it as a part of our gbuffer is because the geometry path actually already writes there. We write there all our indirect lighting and all the scene reflections, all the ambient colors, pretty much everything that can be done at constant time at the beginning, we put it there. The indirect lighting we have is stored in light maps. For static objects, we use YUV space and S3TC5 textures for nicer quality. And for dynamic objects, we use spherical harmonics, and we generate image-based lighting textures later on. So whenever you see IBLs, it's image-based lighting. Well, I mean, again, I have to refer to Michiel's talk yesterday. He talked about it. But if you missed it, just grab me sometime and ask me what we do there. And later on in the lighting path, we add all the dynamic lights there. Then the last part of the G buffer, which sits in alpha channel of the accumulation buffer, is a glow. Glow is pretty much our last thing that remains from our HDR pipeline. It is scaled luminance of the light accumulation buffer. So every time we add something to accumulation buffer, we just update the glow. We have something in range, I think 0 to 4, and we use it later on to add bloom in post processing. But also, actually, and that is maybe more important, we use it in motion blur and depth of field effects to actually have some kind of HDR color. So if you make a blurry region in depth of field and you would just use the light accumulation values, it would just dim the lights. If you have bright color, it would just dim. But then it's a hack. We just multiply it with the glow value, and it shines. We have a nice HDR looking bokeh effect. So I was talking too much. Let's have some pictures. This is actually how the lighting accumulation buffer looks after the geometry pass. So you can see that it is actually pretty well lit scene, I would say. All the characters have nice normals, have depth in there. We could pretty much I think we could even ship with this. But we added the real-time lines, of course. This is what I will be talking about later. And okay, so to wake you up a bit, it says there that it doesn't have textures. Yes, the right part of the screen doesn't have, the left part of the screen doesn't have textures, but who actually noticed that the right part still has some textures in there? Nobody. So I think we can spend our texture budget next time on something else. Lighting pass is very expensive, really. We have hundreds of lights on screen, tens of them. Shadow casting is it's pretty much a mess. It's uncontrollable. There are some scenes where we have more than 300 lights at the same time on screen, and without the differentiating, we would not be able to do anything with it. And of course, we tried to be cool, so we added anti-aliasing there, and that just means we have to shade everything twice. So we had to be quite clever to do our optimizations, and we are actually pretty lazy bunch, so we try to avoid the work where possible. And if we have to do some shading, then we actually try to use the fact that we have MSAA. MSAA is multi-sampling anti-aliasing, something like that. So we try to use the fact that we have MSAA, and we try to work actually less for it. So we try to get it as close to the coast of non-anti-aliased image as possible. And of course, we try to pre-compute some data. I was talking about the sun shadow buffer. This is pretty much it. And if everything else fails, we try to hack our way towards 30 FPS. So that's our approximation pass. How to avoid the hard work? Well, the first thing, and actually it's pretty important for us, it's not to run shaders where possible, because in deferred shading you run lighting in screen space. So you can have nice light on the screen, but it can be behind the pillar. So it just doesn't contribute to any of the lighting you see. But if you're not clever, you will actually run shaders on it. The same goes. You have a hallway. You have a light that shines from the top, and it affects all the pixels. But in the end, it just lights some air. So you want to skip that. And that's where we found out that it's really important to have your early depth and stencil units working. We got burned so many times on this because you just expect them to work. No, you have to care them, feed them, and actually check every month if it still works. So what we do is, instead of just rendering some quad on screen and for each light and trying to find out if the light actually affects given pixels, we use 3D representation for the lights. So, for example, point light is just a sphere, as you saw on the first images, and this allows us to actually use early depth and stencil culling, because for the first in the first pass for each light, what we do, we render the back faces of the light with greater equal depth test, and this pretty much marks in the stencil all the pixels that are either in light or closer to you. And then when we do the final render, we render the front faces with depth test set to less equal. And this actually, and we use the stencil result from the previous pass, so this actually closes the volume for us, and we lit precisely the pixels that are inside the light volume. But this can be sometimes expensive, because just having separate stencil pass sometimes is not good. So what we use is a cool thing called the depth bound test. It's cool because it actually doesn't need your fragments to do the test. You say, I want to render only pixels that are within min and max Z range, but it actually does a test on values that are already in the Z buffer. So no matter what you pass into the pipeline, if at that pixel the Z buffer value is out of the range you specify, it will reject the pixel. That means we can reject the light very quickly, because we just before we render the light, we just find out the min and max Z value for the light, set the depth bound test, and if the light doesn't affect anything in that range, it will just get thrown away. So it's pretty good if your hardware supports it. And the last thing is we try to use conditional rendering where possible. Conditional rendering allows you to run a fragment query in one pass, and in the next pass you can say, okay, I want RSX to skip this part of the display because the fragment query returns 0. So what we do, if the light is not visible, which we discover in the stencil pass, we do not render shadow maps. We do not render the final expensive shader. So pretty much we do not have to be very precise with the culling, because all our lights that are not visible will be rejected very quickly. And yeah, so this was how to not run the shaders. But what if you actually have to run the shaders? We still have some options there. And that is, of course, once again, thanks to deferred shading, we can have optimized shaders for each light. So if the light doesn't need specular color because it just has 0 specular color, or it uses only 4 shadow map taps instead of 8, we have a special shader for that, and we are able to pick it at runtime, depending, for example, on the distance of the light. And this is how we keep our performance higher, and we actually do not lose quality that way. And the cool thing is that even though you can think about, yeah, I will have a lot of combinations of all the different features that the light can have or might not have, it's still less than what you have in your average forward render as the mess that you end up with all the shader combinations. And we actually use it pretty well to fade out the shadow casting lights. Since we do not have any kind of hard limit on how many lights can be shadow casting on the screen, the only thing we do is we say, if the light is at 50 meters, we will start to fade out the shadows. When the shadows are not visible, we will switch to cheap shader without shadow casting. Everything is fine and dandy. And of course, since our artists are the control freaks, we gave them the values, so they can play with it. They can set it up as they want. It works pretty well for us. I don't know if it works well for them, but we are happy. And of course, we have something similar for shadow map. If we find out that the object that is rendered into the shadow map is small, either in shadow map or on screen, so it doesn't really produce some nice shadow that you could even notice, we just drop it. That way we try to minimize the vertex cost into the shadow maps. So our MSAA is hard. So first, quickly some quick facts. In MSAA, you don't shade pixels. Each of your pixels consists of some number of samples. In our case, it was 2 samples per pixels because we use quincunx. And each of these samples has to be lit, preferably individually, because they can be different. The good thing is that if you hit a non-edge pixel, both of the samples will be the same, because the pixel shader is always run only once per pixel in geometry pass if it's not an edge pixel. So our solution for this was what we call in-shader supersampling. So instead of running the lighting pass in the doubled resolution to cover all the samples, we run it in the native 1280-720p resolution, and actually do the supersampling in shader. So we load both samples, do two lighting equations, combine the results, output it in one go. And yeah, you might think, what is the difference between this and the regular supersampling where you just touch every sample individually? Well, the lighting cost is, yes, pretty much the same. We do the same amount of work, but what we can do is we can make shadow map filtering much cheaper, and that's what I will be talking about on the next slide. So our motivation is that artists do not define shadow sampling in a way like I want eight filtering tabs for one sample. They actually, the only thing they want is I want filtering kernel to be 3 pixels wide, and we actually pick number of samples, number of tabs for them, and that allows us to just consider the amount of shadow map tabs per pixel. So if they say we want 8 filtering tabs, we know we have 2 samples per pixel, so we just split the kernel into 2. We have 2 disjoint sets. We compute shadow mapping for each of these samples separately using appropriate set for it, and at the end we combine the result. The good thing is it's as fast as non-MSAA case. You never do more than 8 samples per pixel. If it's non-edge pixel, then G-buffer values are the same, so you end up actually with the same shadowing quality as non-MSAA case. If it's edge pixel, then of course you have half of the filtering tabs per sample, but honestly, you don't notice it. So I talked about the sunlight at the beginning. We store the special sun shadow buffer for it. So yes, it makes sunlight pretty special for us, and the reason is that it's full screen directional light. Full screen with deferred rendering and MSAA, that equals panic, because it can just touch every pixel on the screen. You don't have any mean to do something about it. If in the worst case you just have to shade all the pixels, but we at least try to be clever and make the average case a bit lower. So what we do, we render the sunlight not as a single full screen quad. We render it in multiple depth slices, and this allows us to trade quality for performance. So for further slices, we can have a lower resolution shadow map if we want lower amount of shadow filtering tabs, or we can drop the shadows completely if we decide. And as it gets closer to the camera, we bump the quality a bit more. And again, this is a fine example where you can use a depth bound test, because you can always just render the full screen quad at the near plane, and if we set depth bound test for the min and max of given depth slice, it will reject in early zcal all the pixels that are not within that depth slice. Sorry. Yeah. So I finally get to those sun shadows from G-buffer and what we use it for. So I said we store the direct sunlight shadow there, and we use it to eliminate the pixels that are not lit by sunlight. So what we do, we have a special pass that takes the sun shadow from G-buffer, runs over the screen, and stencil marks all the pixels that do not need expensive real-time shader, because they're in shadow. And we also, I said, mix them with the real-time shadows to get a bit of more quality. I will have some images to show this. So this is our final scene. It's from Corinth River level. This is how the sun shadow channel looks like. You can notice it's actually pretty low resolution, but what you can also notice is that more than 1/3, maybe even half of the screen is in shadow. So when we run the stencil pass on it, the red pixels are the pixels where the expensive sunlight shader will not run at all. What you might notice is that characters stayed white, no matter if they're in shadow or not, because we only do this for static objects. Characters have IBLs, and actually what we do in some where we know that we have some dark area, we have IBLs that are able to write dark colors into the sun shadow buffer, so we can actually sometimes shadow the characters, reject the characters in shadow as well, but mostly we don't do that. And this is when we start to render sunlight. This is actually the scene where we have only the depth, the very background slice with no shadow at all. Then we add the slice number 2 with shadows, and as we go closer to the viewer, we add more and more. And this is our final image again. This is how it would look without the sunlight shadow. I made a circle there. What you can notice is the box, the obstacle is shaded differently. You see some normal popping in, which is actually correct. You would want that. You see some glowing edge on the left side, which is imprecision of the shadow of the real-time shadow map. And what you probably didn't notice is that ambient occlusion got gone. So we actually used the sunlight shadow, shadow channel to add very cheap ambient occlusion to the screen for static objects. And yeah, the result, I would say, is pretty good. And I was talking about some approximations, so this is our fake MSAA. We use it only for distant pixels, so you don't notice it. And what we do is that we actually read the albedo and position from the G buffer for both samples, and we do proper shadowing for both samples. But then we switch to higher gear, and we actually throw one sample away and do only single lighting equation. So we only take the closest sample, compute the equation there, and then we just treat this result as if it was computed for all samples separately, and we add the shadowing on top of it and output it. It actually works for non-edge pixels, of course, because the G buffers values are the same, so the result doesn't change. But you might think, yeah, how can this possibly work for the edge pixels? And the short answer is not. It's just a hack. We put it there, nobody noticed, and it's stuck. But it has some motivation why it's there, because we use it on the furthest depth slices, and the most prominent edges you see there is geometry against the background. The background is for sunlight. The background is always in shadow because the sun shadow value in G buffer is 0. So you get 0 multiplied by that fake equation that didn't belong to that sample, plus the correct shadow and correct equation for a closer sample, which is seen geometry. So there it works. It also works partially because we still have some anti-aliasing there. We still have per sample information from the geometry pass. We still use separate albedos there. So if the samples are sufficiently different in albedo, you just don't notice it. And of course, our scene is heavily post-processed, so we have either depth of field at the back, or we have a lot of particles and smoke in front of it. Yeah, so we get away with it. Sorry. Now I'll talk a bit about the shadow map rendering. We generate the shadow map for each depth slice of the sunlight separately. You can think about it as cascaded shadow map is pretty much it. And the common approach you would choose is you try to align the shadow map to either view direction or to some edge of the depth slice region to maximize your shadow map space. That's the picture at the bottom left, where you have view frustum and imagine the light shining from the top. So you align the shadow maps like this. The problem is you rotate, you regenerate the shadow map, and then it stops to work because as you rotate smoothly, you regenerate shadow map every frame, and you get sub-pixel motion in the shadow map, and it will result in the shadow shimmering. I have a little video of it. You can notice at the lower left corner how it shimmers. This is actually not something you would see in our game because we have that sun shadow there, which would channel there, which would block this a bit, and we have much more filtering. This was an example to show you how it looks. So yeah, it's pretty brutal. And what we do? Well, we try to fix it by actually removing the rotation from the shadow map at all, so completely. So we find the bounding sphere of the region which the shadow map should affect, and we generate it only once, and we never rotate it relative to the world. So no matter how you rotate, the shadow map will stay the same. And what we also do, we prevent from the sub-pixel motion in the shadow map by actually, I have to describe it as we snap the shadow map always to the next pixel. So pretty much if your motion within the shadow map is less than 1 pixel, it will always get rounded to that pixel, and that's what makes the shadow maps stable. There is a paper about this in Shader X6, so if you want more details, look there. And also, I have to say, a disclaimer, these are not the pictures from our next game. And this is fixed. You might notice in the left corner one of the pixels still blinks. That's my error that I made when I made this video. And you notice in the shadow map on the top right corner as it jumps, camera moves smoothly, but the shadow map actually jumps. It jumps by 64 pixels just to emphasize this effect. Normally we just move it by exactly 1 pixel. So, end of the nice graphics. Let's move to the SPU rendering and memory allocations. I said already at the beginning that we use multiple SPUs to build our push buffer. We use SPUs to generate the geometry pass. In parallel, there is an SPU that generates the lighting pass. Then there are some SPUs that generate the shadow map that are launched from it. And then we, of course, have a whole bunch of SPUs that generate vertex arrays, generate those image-based lighting textures. And this all needs to happen within the frame, but it's all temporary data. As soon as RSX is finished, the data should be reused. So there are two common techniques that you usually employ. One is ring buffering, where you have a single buffer, you progress with filling it, and then there is RSX that goes from the other, follows you and eats it, and you can pretty much reuse the memory. The problem is what do you do with out-of-order allocations. If you build your push buffer out of order, ring buffer will not work for you. So the other solution is double buffering, where you are pretty much free to do whatever you want within the frame, but you pay for it by having double amount of memory. So what we did is we tried to have something similar to ring buffer. So we have a fixed memory pool, which is for Killzone 22 megabytes. We split it into 256K chunks, and each of these chunks can be allocated separately. So each of the chunks has what we call allocation ID, which is something that a client, in our case, either a vertex, skinning vertex code or push buffer SPU. This is what it passes to the allocator, and we store it for each block. And then we have one global, which we call free ID. That is the ID of the free block, of the last free block. And to make things very simple, if allocation ID of the block is smaller or equal to the free ID, the block is considered free. So, and yeah, I didn't mention the it is the RSX that actually frees the memory. So instead of on SPU saying this block is free, we just say this block at this point in the frame is free, and it's a command to RSX that just fills our free ID value as soon as it passes the point. So what we gained? We got all the strength of ring buffering with none of the weaknesses. We can allocate the memory from PPU, from SPUs, out of order. It's a lockless algorithm. It's pretty much just a walk over the table with those allocation IDs and try to find the one that is free. So all the SPUs can just run at the same time. They allocate the memory as they want. And as RSX eats the frame, it will reuse those. They are once again able to reuse the memory, because we try to allocate this memory just in time for RSX. We are always 1 or 2 blocks ahead of RSX with our push buffer generation. So, for example, just to illustrate it, we say that we are going to use 1,000 of these allocation IDs per frame, and we know that geometry pass will be at the beginning of the frame, so it will use the first 100 allocation IDs. Then the lighting pass, which is a bit longer, is somewhere in the middle of the frame, so that one will use IDs from 100 to 800, let's say, and the rest of the scene, forward rendering, will use the rest of the IDs. And lighting pass is free to distribute the IDs as it wants for the shadow mapping. This allows us to know what memory will be free at which point in the frame. So, for example, for skinning, we can run all the skinning jobs at the very beginning of the frame in a bulk, and even though we don't have any displays generated, we already know that, oh yeah, we have this mesh, it casts shadows, it is not transparent, so the latest point where it can be used in a frame is after the lighting pass, because it needs to be in shadow. So we give it the allocation ID of those 800 that I said, because it needs to survive till the end of the lighting pass. If it doesn't cast shadows, we'll free it right immediately after the geometry pass. So it really simplifies our engine. And this is some specific example. Let's say it's our geometry pass. So we want to generate the geometry. We allocate the first block of memory, and we give it allocation ID of n. The thing is, it's not nth block in that memory pool. The position of the block in the memory pool doesn't really matter. What matters is that this block at some point will have ID n that we store in the table. So we have it. The first thing we do, we put a GPU stall there. This is a command that instructs GPU to wait until we fill it. So we fill the buffer. We reach the end, but we have still something more. So we allocate the new block. We give it allocation ID of n plus 1, so 1 higher. And again, it doesn't matter where in the pool that block is. It's just some of those free 256K chunks that we have. And what we do first, we say the first command is free the previous block, because when you reach this, you don't have to worry about what was in the previous one. And again, we put GPU stall there, so RSX will wait until we fill the buffer. Then we are free to connect these 2 blocks. So we instruct RSX to jump from the old one to the new one, and we remove the old stall. So if there was RSX waiting at that point, it will now consume the first buffer, jump to the next one, free the previous one, and wait again until we fill it. And we do this until we generate all the display list. The thing is, there are those waits, and you might think, yeah, okay, we have RSX stalling. It's not true. I said we are always, or we try to be 2 or even more buffers ahead of RSX. So when RSX actually hits the buffer, it's usually already without the GPU stall, and it can be just immediately processed. To make things a bit more confusing, we do not use that memory only for push buffer. We do write push buffer data there, so we do write draw commands, But at the same time, we reuse the same memory from the other side to actually write rendering data there. So if you have a object that needs that IBL, we reserve memory at the end of the buffer. In our case, it's 8x8 texture, and we launch SPU job to fill that texture. And we know that this texture will be used for the draw command. It doesn't have to be only graphics data. We for example, store there the whole buffers for scene graph queries. And as we put more and more draw commands there, the block gets filled slowly. And when they meet somewhere in the middle, the block is full. We allocate a new one. What this allows us, it might sound complicated, but what it allows us is to keep memory local. So we try to keep all the draw commands and all the data that belong to those draw commands as close in memory as possible. And this is the best case because in this case actually they live within the same block. So as soon as RSX is done with this block, we have no memory waste. All this gets thrown away. Think about it. So my conclusion. I don't know if it sounded like this, but we try to keep it simple. Actually, yeah, the Killzone 2 engine is really simple. We use the deferred shading. It allows us to keep all the rendering paths very simple, very straightforward. And I actually hope that I gave away some of those simple tricks, so you can use them for our next game if applicable. And thank you very much. So we will have time for some questions. So if somebody wants to ask questions, could you please just walk to the microphone? And also don't forget to fill the forms that you've been handed. So the question was if we were able to move something from forward to deferred that would just belong to forward. Yeah, we do that for sheets and decals. That's all the posters and bullet shots on the walls. Those, even though they are transparent, they render in the deferred path. The reason for this is that we can then use dynamic lighting on that. So we just put a bullet hole on the wall, write out the normal map, blend it with albedo, and the good thing is it actually shares the indirect lighting from the G buffer, so we have the bullet holes nicely blend into the scene. Okay, good question. I actually did have like 3 slides about this, because the fact is we actually started with light pre-pass rendering. That was I guess our first year with this, and we were really happy with it. It's really cool way to do it. But the reason why we don't have it in the end is we just started to put more and more additional data to the G buffer. So it just started to grow. We put motion blur there. We wanted to have that sunlight buffer there. So the first pass became really expensive, and still the okay. Just for those who don't know, light pre-pass rendering tries to simplify these deferred shading by actually lighting only, let's say, normal. So you don't have any information about your diffuse textures, anything in the lighting path. Just do simple lighting equation, accumulate just light colors, and then you have another pass similar to the geometry pass that actually scans this and renders the real material. So it's very close to forward rendering, but you don't have to do all the combinations of lights in your shader. You just take the value from the G buffer as a light intensity, and in your last pass you just render the material. So you pretty much have similar shader to forward rendering. And as I said, we had it. the biggest problem for us in the end was performance, because having 2 complete geometry passes was just too much for us. But should it work, it is very nice. For us, it is a very nice technique.
I was going to ask, you're only using 8 bits per color channel for your lighting buffer. Are you able to avoid overflows and things like that without clamping problems?
We don't. There's the thing I said. We have the color correction filter, and it just the thing is, in different shading, if the light accumulation hits 1, it just stays there, because you do not do anything with it afterwards, like with light prepass, where you afterwards multiply it with albedo. We have always the final value there, so if it just hits 1, it will probably stay there. And since we don't have any of those automated tone mapping, we do not darken the scene. So yes, in some cases when they make the color correction filter darker, you will see the clamping, but that's it. And as I said, we have the glow intensity. That one is allowed to go above 1, and if it hits values about 1, it's usually something that glows on screen. So it gets picked up by post processing, and it will keep it about the like higher intensity.
So now we know that you tried light prepass and it didn't quite work. Any other approaches would you try that didn't end up working?
We actually did have a version of the engine that didn't have specular lights. We only had diffuse lights, for example, and it's just we wanted to have nice shadowed speculars, so we started to mess around with it.
So with your specular lights, the light itself determines whether or not it reflects off the materials in the scene. Is that accurate, or do the materials define whether they're reflected?
The materials have specular the shininess, the specular intensity, and also the roughness, which is how specular they are. But that's it.
It seemed like there was a point where you were saying that when the light is going into the scene, it also determines whether or not it's going to specularly reflect off materials.
Oh no, light always does it. Light doesn't know what the values are in the G buffer, so it always reads it. You were probably talking about the light, the shader combinations I was talking about. Yeah, if the light can, the artist can define properties of the light. So if they say that this light will not affect specular at all, it will just do the endodel, the diffuse calculation, and it will not touch. It will not add specular contribution there at all. So it's per light. In this case, it's per light property. Yeah.
I mentioned you used the stencil a lot. Did you find any problems with clearing the stencil quite a bit for each light and all that kind of stuff?
No. We used RSX as memory compression, so we use it's pretty much the same thing that they tell you about PC, that clears of the full screen stuff is almost for free. There is acceleration for that. All right then. Thank you very much. And yeah, if you want to ask something more, feel free.